For years, drone aviation was defined by an invisible leash. A drone could only fly as far as a direct radio signal reached. Today, that same hardware is capable of crossing oceans, maintaining a continuous telemetry link to a satellite constellation hundreds of kilometers above. That original tether is known as visual line of sight, or VLOS. It restricts operations to a specific radius around the operator, placing a hard ceiling on the geographic reach of delivery networks, pipeline inspections, and maritime surveillance. Reaching the multi-billion-dollar valuations predicted for the drone economy requires crossing a specific threshold, beyond visual line of sight, or BVLOS. This allows a drone to navigate and communicate far past the horizon of human observation. Industry observers often cite battery energy density and airframe aerodynamics as the primary barriers to scaling these operations. The actual constraints are found in the digital infrastructure. The barriers to a global fleet are communication latency, congestion and unlicensed radio frequencies, and a dangerous dependence on fragile GPS signals. The solution is a hybrid connectivity architecture. This system routes data through non-terrestrial networks in space and utilizes quantum-enhanced sensors to maintain navigation without any external signals. Scalability is determined by the quality of the network architecture and data pipelines, rather than the aircraft itself. To understand why this network architecture is so difficult to build, we have to look inside the drone's onboard flight controller, the embedded computer acting as its nervous system. The flight controller relies on a proportional integral derivative, or PID, control loop. It continuously reads sensor data, calculates the difference between its actual position and its desired path, and sends hundreds of micro-adjustments per second to the motors to maintain stability. This chart plots communication latency against orbital altitude. For a remote system to safely direct that high-speed PID control loop, it requires a round-trip latency of under 50 milliseconds. That red line represents the absolute physical limit for safety-critical autonomous control. For decades, global satellite communication relied on geostationary, or GEO, orbits. These satellites sit nearly 36,000 kilometers above the equator. A radio signal traveling to a GEO satellite and back must cover over 71,000 kilometers. Even at the speed of light, that journey takes roughly 600 milliseconds. That delay exceeds the safety threshold, rendering geoconnectivity useless for the real-time control of a fast-moving aircraft. Constellations in low Earth orbit, or LEO, solve this distance problem by operating at altitudes as low as 550 kilometers. Because the satellites are physically closer, the round-trip latency drops to between 20 and 40 milliseconds. This places the signal securely within the requirement for real-time drone control. With latency minimized, geography becomes irrelevant. A commander operating from a control room in one hemisphere can pilot an aircraft over a different continent entirely, analyzing high-resolution video feeds with zero perceived delay. Low Earth orbit connectivity decouples a drone's operational range from local, ground-based cellular infrastructure, enabling global reach. Utilizing these LEO networks initially came with a weight penalty. Traditional systems require specialized terminal dishes that are far too heavy for small commercial drone platforms. The breakthrough is direct-to-device, or D2D connectivity. This allows the standard 5G modem already installed on the drone to communicate directly with satellites in space. D2D is built on the 3GPP non-terrestrial network, or NTN standard. This framework adapts terrestrial 5G rules to the extreme physics of the orbital environment. This animation illustrates the primary physics hurdle the NTN standard must overcome, the Doppler shift. A LEO satellite moves across the sky at approximately 7.5 kilometers per second. Down in the atmosphere, the drone is also moving at high speeds on its own independent vector. This compound opposing motion violently compresses and expands the frequency waves. For a standard 5G receiver, this constant shifting causes an immediate loss of synchronization, breaking the communication link. The NTN standard solves this mathematically. The system uses precise satellite ephemeris data, exact calculations of the satellite's position and velocity to predict the frequency offset. It then pre-compensates by calculating the inverse wave before the signal is even transmitted, locking the frequencies perfectly into place. By managing these physics in the software layer, the NTN standard turns a lightweight 5G chip into a global communication node, removing the need for heavy satellite flight hardware. Global connectivity only matters if the physical airframe can survive the journey. As fleets scale to hundreds of simultaneous BVLOS flights, managing hardware failure becomes a data problem. Operators are increasingly relying on drone digital twins. A true digital twin isn't a static 3D model. It's a continuously updated, physics-based simulation synchronized with the physical asset in the real world. This schematic breaks down the architecture of a digital twin into 4 distinct layers: the geometric model, the physics simulation, data synchronization, and intelligence. While a drone is in flight, the data synchronization layer ingests real-time telemetry from the aircraft's sensors. This includes minute-by-minute updates on motor currents, battery voltages, and vibration signatures. That live data feeds into the physics simulation layer. Here, the system calculates the structural stresses and thermal loads that specific components are actively enduring. The intelligence layer processes these simulations to generate a remaining useful life, or RUL, prediction. This calculates exactly how many flight hours a specific component has left before it fails. With highly accurate RUL predictions, an operator can detect the microscopic degradation of a motor bearing and ground a specific aircraft long before a catastrophic mid-air failure occurs over a populated area. Digital twins allow enterprise fleets to replace scheduled maintenance with dynamic, condition-based intelligence. Even with perfect communication and hardware health, a drone is critically vulnerable if it relies on GPS to know where it is. This schematic shows a standard GPS setup. Because GPS signals originate from satellites 20,000 kilometers away, they arrive at the Earth's surface incredibly weak. They are highly susceptible to dense urban shadows, deliberate spoofing, and military jamming. The moment that external signal is lost, the drone's position estimation begins to degrade, creating a widening circle of spatial uncertainty. Conventional mechanical backups, like internal accelerometers, suffer from measurement drift. They accumulate tiny errors over time, effectively blinding the drone's navigation systems within minutes. The ultimate physics-based failsafe for this vulnerability is quantum inertial sensing. This technology utilizes an atom interferometer. By splitting a wave of ultra-cold atoms with a laser, the system measures the microscopic interference patterns created by the aircraft's acceleration and rotation. It calculates movement based on the fundamental laws of motion. These quantum sensors measure forces with an accuracy 10,000 times greater than the best conventional mechanical accelerometers on the market today. At this level of accuracy, sensor drift is virtually eliminated. A drone can navigate flawlessly for hours in GPS-denied or electronically hostile environments. Quantum navigation severs the drone's final reliance on vulnerable external infrastructure, ensuring absolute physics-based autonomy. These technologies move the sector from isolated breakthroughs to a macroscopic shift in industrial capability. This is the drone connectivity evolution model, charting the development roadmap for the sector. The industry currently sits at the threshold between Generation 3 and Generation 4. We are moving past cellular networks backed up by high-latency geosatellites into a framework anchored by hybrid LEO networks. The final architecture arrives at Generation 5, where NTN-native direct-to-device 5G and 6G provide ubiquitous, seamless global coverage without extra hardware. In this environment, a drone will navigate dense urban air mobility corridors using terrestrial 5G, and then seamlessly hand off its telemetry to a LEO satellite as it crosses oceans or expansive rural expanses. Throughout the flight, predictive digital twins ensure the physical hardware survives the journey, while quantum sensors guarantee precise navigation regardless of the environment. For enterprise and defense leaders, the competitive advantage in aviation is no longer found in building a slightly more aerodynamic airframe. The advantage belongs to whoever builds the superior network architecture and data pipelines. The drone has shed its origins as a remote-controlled tool. It has become a globally connected, autonomous node, the foundational hardware of the intelligence economy.